So next lecture we talk about the DRAM cell capacitor, and here this is a summary, and I want you to understand the cell capacitor is standing up with very high aspect ratio today. The aspect ratio is approaching like 100, and then we need to maintain the cell capacitance. Let's say about 5 femtofarad, 5 to 10 femtofarad in that range, to have enough sense margin. And then this require the EOT of the dielectric to be about like 3 to 4 angstrom in terms of the equivalent oxide thickness. And then the leakage current needs to be maintained very low, below like 1e-7 ampere per centimeter square. So this is the cell capacitor, which is one part of the DRAM structure, right? Because the other part, as we know, 1T, 1C, then we need to look at the transistor technology as well for the DRAM. So that's today's topic. So before we talk about the transistor, the sense margin, as we discussed before, right? Delta V depends on the cell capacitance and then the ratio between the cell capacitance and the Bitline parasitic capacitance. So then we talk about the cell capacitance, right? How to maintain that by stacking this cylinder very tall. And then on the other hand, you may wonder, then we may have some solutions if we can reduce the Bitline capacitance, right? So here, actually, this is a breakdown of the Bitline capacitance. There are many components contribute to the Bitline capacitance. So if you think about the Bitline here, we have this storage node capacitor, right? This capacitor is standing up here, and then we have this transistor here. Actually, the transistor, we will talk about that in the next few slides. So it's a buried channel transistor. So the gate is here. So basically, transistor is like this gate, like your drain and source, right? And then the source, you have the Bitline contact, BLC contact, then attached to your Bitline. So then here, your Bitline capacitance is all the components that attach to the Bitline, right? So you need to look at all the capacitance that are attached to the Bitline. So what do you have here? For example, from the Bitline contact region, you will have this number 1, Bitline contact to the gate coupling. So you have some capacitance here. And then your Bitline contact, of course, is the junction. Then you have the junction capacitance there. And then your Bitline itself, your Bitline will, pass, let's say, adjacent to the stand. You have here, you have the standing capacitor, right? Cylinder. So your Bitline will be adjacent to that. Then you will have this coupling from the Bitline to the storage capacitor. And then, of course, between Bitlines, from wire to wire, you have the isolation, then you have the capacitance. So all those capacitance will add up together as your CBL, right? So here in this pie chart, we show the breakdown, and the majority of the Bitline cap is contributed by the number 1, this Bitline to Merline cap, which is this part. And then number 2, the Bitline to plate, which is because this is plate, right? On the other electrode of the cap is plate. So it's the Bitline to the storage node capacitance. Okay. So we have to reduce this capacitance if you want to maintain the sense margin. Of course, we want to increase the CS or at least maintain the CS. Then if we can reduce the CBL, that will help. So one solution to that is here. You see the capacitance depends on the dielectric between those two plates, right? For CS, you want high K dielectric in between. Then for those parasitic capacitance, you always prefer low K, right? Low K dielectric to reduce those capacitance like 1 and 2 here. If you can feel the isolation with low K material, that will help. Okay. So question?
Last class you mentioned that the CBL generally doesn't scale, right?
Mm-hmm.
So which of the components is doing that, or all of them the reason for that?
Yeah, so CBL, for example, the number 3 does not really scale. So the wire capacitance typically is 0.2 femtofarad per micrometer, regardless of the technology node. And then the other component here, we're going to show you the innovations in the design to try to reduce that, okay? If you do nothing, then they will not shrink, okay? But in the next few slides, we will show you some strategies. So first one is the air gap. So here you see that the Bitline to the storage node, we used to have this number 2, right? Number 2, which is a big component here. So if you use air spacer here, so basically you create some void in the structure, and you have some nothing here, basically air, nothing. Then air's epsilon is close to 1. So that will help. Actually, that's a ultimate solution. That's the lowest capacitance you can get by introducing the air gap. So this was adopted in around like 20 nanometer technology node. The air gap is used to reduce those capacitance. Okay. So you have to etch those materials away. So any questions? Then
Here is dielectric. There could be an issue, right? Like this, some instead of air, can we use helium or something? Because there could be some impurity issues, which could
use what?
air could have its own impurities, right? When we
Air has impurity. What kind of impurity? Air is nothing. It's a void there. It's a void here. That's nothing. Okay. When we say air, means nothing. Nothing is there. It's like a vacuum. Of course, you can have some air there. I mean,
We are using the air spacer both to reduce BL to PL and also BL to word line.
no, BL2 word line, we will talk about that in the next few slides. That relates to the transistor structure. So I'll talk about that number 1 component for in the next few slides, because we need to first understand the DRAM transistor first. So here, the DRAM transistor, okay, is different than the logic transistor. It's a totally different animal here, okay? So logic transistor, we have talked about that before in the SRAM lecture. We try to improve the current density, right? So the high performance logic transistor can go up to 2 milliamp per micrometer in terms of the on-state current density. And then we know the industry has gone through the transitions, right, from the planar to the FinFET, and also introduced the high-k metal gates. And then we have this logic transistor today, right? So it's very thin EOT, and then the FinFET structure. So DRAM access transistor is different. This 1T, 1C, this T is more equivalent to today's, like maybe in terms of the performance, it's more like 65 nanometer logic transistor. Even for today's most advanced DRAM access transistor, the performance is more equivalent to old logic transistor. The reason is that the DRAM access transistor is optimized for low leakage instead of high performance. Okay, why low leakage? Yeah, we know that data retention, right? So the requirement for the DRAM access transistor leakage below 1 femtofarad per micrometer. So the logic for high performance logic, on-state current is like this one, off is roughly, of course, depending on the VTH, you have different flavors of the logic transistor, right? High performance transistor or the low power transistor. But even the low power transistor, the I off is like 10 picoamp per micrometer, around like 1 pico to 100 pico in terms of the off current density for the logic transistor. DRAM transistor uses this number is 3 order or 4 order magnitude lower in terms of the leakage current. And then we only need NMOS here, 1T, 1C, that is NMOS, okay. So then we also will need to allow the gate overdrive. If you recall, the VPP voltage is 1.8 volt, for example, right? So then we need to sustain high gate voltage as well. So the DRAM transistor is more like this one, okay? So it has a recessed channel. What does this mean? So here, what is L in this? This is a cross-section view. It's like conventional buck planar transistor, right? Transistor before is like this, right? But then in the previous logic transistor, then this is your L. To minimize the leakage current, you need to increase L. So how do you increase L? You make this recessed channel. So the L is this one, right? So you intentionally increase the distance from source to the drain by recess the channel or recess the gate into the substrate. And also the oxide thickness is thicker, this oxide, to sustain higher overdrive voltage compared to the logic, high performance logic transistor. So this is a key difference. This is to enable this ultra low leakage. Okay. Any question here? Okay, so then let's look at the innovations for the DRAM access transistor over the generations. So this recessed channel, recessed gate was introduced around 19 nanometer technology node. And then at 45 nanometer, this saddle FinFET was proposed and used. So still we want to control the short channel effect. So we want to have FinFET. But then this saddle FinFET is a combination of the recessed gate and then the FinFET. Do I have the, let me see. Yeah, I have that in more details in the next 2 slides. But this was another innovation. And then we have the buried gates. I will talk about that in more details as well. So today's access transistor has those features: recessed channel, buried gate, and saddle FinFET. And we will talk about the next generation later, which will transition to this vertical gates. But we will talk about that after we finish what is used today, and then we talk about what's the future. So First, this recess gate or recess channel introduced by at 90 nanometer node, and also this is called the RCAT, recess channel array transistor. So we show this recessed channel, right? So then the gate is here, and then your word line is here, and then you have the source and drain, and channel is effectively increased in terms of the length. So by doing so here, for example, in this this was introduced at 90 nanometer node almost 20 years ago. So then the data retention time improved because the off current is reduced. So here, this is from this paper, VLSI 2003. And then this is distribution of the retention time. And you see that by introducing this technique, we can improve the retention time. And then this saddle FinFET. So what is that? So it's like a fin. So here from the AA direction, it's like a fin. But then it's like the saddle. You know, saddle is if you have ever ride a horse, right? It's something you ride on the horse. Then it's like you are riding on the horse like this. Okay. So it has the buried gate or recessed gate here. Okay. So here from the, let's say, BB direction, you will have some recessed gate here. So FinFET used to be like this, right? So then you have to, recess this fin a little bit and then try to, gate is try to couple the channel deeper into the fin. So it's a combination of the FinFET and the recess gate, basically. It's hard to visualize the 3D structure because I don't have the animation, but you can imagine. This is something like you are riding the horse. Saddle means recess gate plus FinFET. So the FinFET, is to improve the short channel effect. And also improve the drive currents, because still we need certain unsteady currents to allow fast read. So by FinFET, FinFET improves the unsteady current density as well, right? So here you see the unsteady current density also improve. Okay, then the next strategy is this buried gate. And if you recall the component number 1 in the parasitic capacitance, that is this Bitline contact to the word line, which is here. So this is what we have before. So the word line metal, and then the poly gate, and then this is WL. This black one is the WL in and out of the plane, right? And then we have the poly gate, and then we have the gate oxide somewhere here, and then you have the recess channel. So then you have your contact, Bitline contact here, right? So we have this overlap. That is this number 1 component in the parasitics. So here the idea is to get rid of this polysilicon, try to bury the metal, the word line, underneath the surface of the silicon. Right, so basically here is like you are doing this one. You are burying this, basically remove this word line, but try to bury the word line into the silicon. So that will increase the distance between this word line and then the bitline contact. So you reduce the overlap. That means you reduce the capacitance. Okay. So here you see the capacitance greatly reduced. So this is another way to improve the sense margin. Right? So we talk about those innovations over the generations. If you combine the innovations from both capacitor and transistor, then this is how we maintain the scaling, right? So for the capacitor, then higher and higher, and then for the transistor, we're trying to have this resist channel and then try to bury this word line. So this is what we have today. Okay. Any questions?
Is it fair to say that in buried style, the L effective reduces?
What's your question?
Because in buried you're pushing the poly, right? Would the L effective of the channel reduce so the leakage will increase?
No, the channel is still like this, right? So it's just bury the word line down to here. Okay. You replace that with some metal or gates instead of poly gates. Okay, so then we will show you some challenges. Okay, moving forward. So even though we say today's DRAM cell is a 6F square cell, and this trend actually is deviating from this 6F square below 20 nanometer load. So here we have this layout, and in the last lecture, some of you asked about the angle. So this angle is decided by the manufacturer. Okay, it's not fixed in terms of this channel orientation, right? So here it says that because the word line pitch poses a lower limit due to the series short channel effect and also the row hammer effect. So basically, the word line to word line coupling has some limitation. Therefore, you cannot place the word lines too close to each other. So as a result, this force the active island, which is the active region. In this case, is a blue region. Align more parallel with the bit line. That means this angle becomes smaller. Right? More parallel means more parallel. Okay. To the bit line. So you have as a result, the actual F square is going up. So this happens in the recent few generations. Okay. But still, I mean, in this lecture, when we talk about the DRAM, we still claim, okay, the mainstream is 6F square. But if you really calculate this number for the recent 3 or 4 generations, then this number seems, invalid. So I will show you some actual number. Okay. So here, this is from 3 chips. So this is 1Z node, and this is the 3rd generation of the 10 nanometer class, right? So here you see 1X, 1Y, 1Z. So here the cell size, and then the design rule. 1Z basically means it's about like 16 nanometer. The F is about 16, okay? And then if you really use this cell size number divided by the 16 nanometer square, then you can get this F square, okay? So you see that here the DRAM cell size scaling slows down. Here we have the absolute value, okay? Absolute value. like 84 times 10 to minus 4 micrometer square. Okay, and then if you normalize this number to the f, for example, when z is f, when x, the f is about 19. Okay, when z is about 16. So if you do that, then you see that here, this effective number of f square increases. Right? Used to be like 6. So if you do that from here, maybe it's a perfect 6f square. But then, since this trend does not maintain, if you maintain this, okay, then it will be 6f square. But then here slows down. So if you really do this calculation, then you will get higher f square. Okay. But still in this, in the context of this course, for example, in your homework and exam, when we talk about DRAM, okay, we still say DRAM is 6f square design rule, okay. But this may not apply to the latest results. Okay, so here, this is another very recent data. Okay, I just updated this from the VLSI Symposium 2024. So here you see the scanning, right? And we are at, I think the latest product just announced like months ago is on the 1C node. Okay, 1C node. And then moving forward, we don't know what will happen. So that's why the industry is looking at alternative designs to enable the sub-10 nanometer DRAM technology. And we will talk about some of those approaches in the next few slides. Those are still under active research and development. There's no product yet, but those are the possible roadmaps moving forward. So any questions? Okay, so the DRAM industry is at a crossroad, I would say. So this traditional 1T1C scaling is approaching the end. And the DRAM industry is trying to look at alternative designs. And one of the early concepts, actually we talked about that before, to transition from the 6f square to 4f square, we have to use this vertical transistor as the access transistor. That's the only way to do the 4f square cell. So this was a very early paper, actually published many years ago, VLSI Symposium 2009 by Samsung. So here, the idea is to, instead of the transistor in the silicon substrate, we're going to build the transistor vertically. Okay. If you have the vertical channel transistor and gate all around gate, right, you will have, let's say, a cylinder, basically. A cylinder of the silicon. And then you surround the cylinder with your gate all around gate stack. And then your source drain is like vertical, channel is vertical. Then you can attach this to the capacitor, right, directly. Okay. The drain is attached to the capacitor, which is standing up directly. So overall, here you will only have the 2F by 2F spacing, right? So here you see that the VLAN, right, is controlling all the gates. You have those vertical transistors gates. And then the Bitline here is collecting all the source together. So from the top view, right, you will only have one wire, one VLAN wire this way, and one Bitline wire this way. And we discussed before, so each wire you need the 2F. 1F for the wire, 1F for the spacing. So it's 2F by 2F, you get 4F square. Okay. So the key is to have this vertical transistor. Any questions? So this vertical transistor then is not easy. The reason is that we have to maintain the very low leakage, right? So this vertical transistor, then we do not have this recessed channel. Then it's not that easy. So that's why the research was published, and then there were no follow-ups over the past, almost 10 years. So until recently, this idea became popular again. Okay. So this vertical access transistor, become active research topic again, thanks to the new material, such as oxide semiconductor channel instead of silicon, because silicon, the leakage is a problem. And if you increase the band gap, right, silicon is like 1.1 electron volts. If you increase the band gap to this oxide semiconductor, and for example, here we have indium gallium zinc oxide, which is already used commercially in your display driver circuits, display of your screen. So then this one has ultra low leakage because the band gap is much larger. So the industry is looking at using those oxide semiconductor to build this vertical channel. Okay. There was recent papers from Samsung, SK, and all those companies on this approach. And then this could potentially enable this 4F² vertical transistor cell. So this is the possible path 1. And this is for the immediate sub-10 nanometer node, maybe the first generation of the 10 nanometer node, 0A node. And then the industry is also looking at more aggressive approach. This is a path number 2, potential path number 2. That is this vertically stacked 3D DRAM. So our research group is also working in this domain. And this will enable the DRAM's scaling for the next 10 or even 20 years. This is at a very early stage. I will show you some results for this vertically stacked DRAM. This was a very new concept. And when I taught this course last time, this concept was not there. So this was really just introduced in the last 2 years. Okay. So I will show you what is this. So the basic idea is to rotate the 1T1C by 90 degrees. Okay. Used to be 1T1C standing up, right? Your 1T1C like this. Or even you change it to the vertical transistor will be something like 1T1C, right? But then this approach is totally different. This is to lay down this entire 1T1C horizontally, or sometimes we call it horizontal 1T1C. So you have the 1T and the 1C horizontally. Okay. So you see some schematic like this. So here this T will be manufactured similar to the stack nanosheet we talked about before for the logic transistor. If you recall, how is that done for the logic transistor, the stack nanosheet? Any idea? We'll talk about that in the S1 lecture. Not the PMOS, I mean, just the NMOS, because here we'll just need NMOS, right? So here you have multi-tier. How is that fabricated? Silicon, germanium, epi growth. So same technique apply here, okay? So here you grow the silicon, germanium, and then you do the nanosheet kind of fabrication for the transistor. So the key is that here, you need to grow many layers sequentially, and then use one lithography to etch, to separate those transistors, because you need to eventually separate them, and also the capacitor region, okay? I wish I could, talk about the 3D NAND flash lecture first, because this principle really learned from the 3D NAND process. So the key idea is that we have to make it bit scalable, bit cost scalable, okay? What is a bit cost scalable? This concept was introduced for 3D NAND, but it applied to here. So since we talk about DRAM, about this first. So here, to make the cost low in the fabrication, you have to reduce the number of lithography step or the number of litho mask, because the litho is the most expensive fabrication step. So here, no matter how many layers you fabricate, you want to use one critical litho to do the patterning and etching. Otherwise, if you repeat layer by layer, so if you fabricate the 1T1C layer by layer, every layer, if you use a litho to pattern, your cost will linearly go up with the number of layers. It's not very, attractive. So here the key is that you have to do the deposition, many layers, and after that, one lithography step to etch. Okay, it's multi-tier deposition, one litho, multi-layer etch. This is the key. Okay, so I will show you some more details in the next few slides, but from the architecture point of view, then this is how it looks like. And then here are some differences between those conventional DRAM and this vertical stacked DRAM. So one difference is that the channel, because now it's a stack nanosheet, actually is floating, okay? There might be a floating body effect there if you don't engineer your junction very well. Basically, it's like FDSOI. You do not have your substrates, then you have the whole generation. The whole will be accumulated in the body. That will raise the body potential. So you may have this kind of problem. This is still under research. You have to basically minimize the floating body effects in this kind of design. And this transistor will be double gated or maybe gate all around kind of nanosheet. So I will show you some demonstrations in the next few slides. The first one was reported by Samsung last year at VLSI Symposium. And they proposed two architectures, actually. So here, from the circuit schematic point of view, this is conventional 1T1C array. And then we want to change to this way, okay? So horizontally 1T1C, but we do have two kind of orientation. One is called vertical bitline, one is called vertical word line. So what is that? So depending on for example here, 1T1C, right? Depending on how you align the word line and bit line. For example here, the word line is vertically collected from different layers. They share the same word line. So it's like a vertical word line. And then the bit line is going to be, you know, orthogonal to the word line always, right? If the word line is vertical, then the bit line will be horizontal. Or you can do the other way, right? You can collect all those 1T, 1C horizontally by sharing the word line horizontally. Then at the end of the, you know, the source here, those bit lines should be vertical. Okay. So this is a vertical bit line and the horizontal word line. There would be some differences in the design. And one challenge for this vertical word line is that the bit line now needs to have this staircase contact region. I really wish I could talk about 3D DRAM first, 3D NAND first, because this all those concepts borrowed from the 3D NAND. So here, for the word line, actually you need to make a contact to this word line. You need to have some extension region for the word line for different, for bit line, for different layers. You need to have a staircase region to make a connection to the bit line. So if you look at the extension, it will be like this. The bit lines we need to extend for different layers. You need to extend by different lengths, and then you make the contact via. So you can access to individual bit lines at a different layer. So that will make the bit line length different for different layers. You know, the bit line length different is a warning, right? So give you some warning because the sense margin delta V, right? Bitline capacitance. That means bitline capacitance is different for different layers. So the sense margin is not uniform. For the circuit design, it's not good. So that's why probably we would prefer, we don't know yet, this is still active research. So in the sense margin point of view, we would prefer this vertical bitline design, okay? Because all the bitlines are collected directly up, there's no difference in terms of the bitline to bitline sense margin, okay? So I'll show you some more results. This is from this year's SK Hynix presentation at the VLSI. VLSI is really a good conference. All those good results published here. And later when we talk about 3D NAND, the first 3D NAND paper by Toshiba also published in VLSI 2007. So, okay, so then here, this is the SK Hynix design. And from the top view layout, and we have this BL contact, and then the storage capacitor. So basically you will have this horizontal 1T and 1C. Okay. So from the circuit schematic, this is how it look like on the right. So in the real 3D view, this is how it look like. So you will have this horizontal transistors, and then you have the capacitor horizontally like this, and then vertical bitline. Okay. It's like this one vertical bitline shared, and then horizontal 1T and 1C. Okay. So you can stack many layers. And here are some real images from this prototype. So here, the 1T is here. This is double gate 1T, and then 1C. Okay. So here I noticed that the C is pretty short, right? In terms of aspect ratio, then C, if you just rotate by 90 degrees, the C should be something like this, right? Yeah. So then I was curious. So I met the SK Hynix researcher like a few weeks ago, and I asked him about this question: why this C is so short? He said in the initial design they underestimated the cap, and then the retention time not so good in this initial design. So they admit that the C should be larger. Okay. So they said this was not finalized design. So anyway, in this paper, SK Hynix demonstrated 5-layer, and then also for the peripheral circuits, they plan to do the bonding. Okay, this will also happen in the DRAM. So the peripheral circuits, like your controller and clock, all kinds of peripheral circuits. I don't think the adjacent, like the decoder or SenSamp, will be on a separate chip, but the peripheral circuits farther away, like the controller, I/O, and so on, will be on a separate chip. And then they do the bonding, hybrid bonding. Okay, this is a 3D DRAM die, and then this is a peripheral circuits die, and then this is a bonding pad. Okay, so this is the very recent results just happened, a few months ago. So this is a very active research area, and yeah, my friend at Micron also is working on this. This told me they have 1,000 people working on this. This is a big moment for the DRAM industry, and because the 2D scaling is almost over, and then the DRAM needs to follow the NAND industry where the 3D happens. You may say that, okay, we already have a 3D DRAM. We'll talk about that maybe next lecture. That's 3D DRAM, like HBM. It's not true 3D. Those are pseudo or fake 3D. Those are by bonding, okay? So here we are talking about the monolithic 3D. You are going to stack or sequentially fabricate those DRAM layer by layer on a single die, not by bonding. Of course, here we can bond the peripheral circuits, but the DRAM cell, the array of the DRAM cell array is monolithically stacked in 3D. So this will be a revolution of the DRAM industry. Okay, so any questions? So here, from my initial estimation, I would say that, of course, we don't know about this, how large the capacitance should be. This really depends on how good this transistor is in terms of the leakage. But if you think about the conventional 2D DRAM, okay, so this aspect ratio is approaching to 100, right? So this is like 100. That means this is very long. For example, like a 12 nanometer load, 100 means this cap is like above 1 micrometer long, right? So if we keep this 1 micrometer long cap horizontally, that takes a lot of space, actually, right? Previously, you are doing 1T, 1C, okay. And then this is only like 12 nanometer or something like that. Or let's say 20 nanometer, less than 20. So here my question is that, actually from the footprint point of view, this horizontal 1T, 1C actually is not very attractive, right? If you think about the dimensions here. Here maybe you only have 20 nanometer. Here you have 1 micrometer already. So what would be the selling point for this approach?
You can stack enough so the density for 1 micrometer is greater than if they were stacked vertically.
Yeah, exactly. So the key is that you have to stack certain number of layers to break even in terms of the space, right? So I would imagine you have to stack at least 64, even 100 layers. Maybe 64. But I don't know. I mean, this is still under the research. But my assessment is that you have to stack this many layers to really get density advantage compared to the 2D DRAM at like a nanometer node. So this one you have to stack many layers. Okay. Of course, if you can find a way to reduce this horizontal cap, not 1 micrometer, if you can do it with 100 nanometer, while still maintain your retention, sense margin, and so on, then this break-even point will be much lower, right? Maybe you only need 8 layers or 16 layers to break even in terms of the horizontal space. So those are the question mark, and my research group is working on those questions. Okay. All right. So then let's continue. Future trends. I should not say future trends because I already talked about future trend here. Okay. I should say current trend. Okay. Current trend. That is HBM. Okay. It's fake 3D. So yeah, so here, before we talk about the HBM, we have to talk about some packaging technology. And here from wire bonding to TSV, okay? So if you stack the chips, right? If you have no other choice, then the very naive way is you have those pads here and then you do the wire bonding, okay? Then this is difficult. But if you can make the connections through the silicon, then you will have much tighter or more dense connections. So here, the idea is to go through the silicon to make the wires. And this is called TSV, through silicon via technology. And here on the right are the simplified fabrication flow to do this TSV. So basically you have a silicon wafer, and then you're going to dig some trenches, and then you're going to have some dielectric to fill the trench, and then add some barrier layer, because copper, you need a barrier for the copper diffusion. Actually, even for the back-end line interconnect, you always have the barrier, like the titanium nitride kind of barrier to prevent the copper to diffuse, because copper is actually very fast diffusive material. If copper diffuse into your silicon transistor will be, short circuit, essentially. So you have to basically coat the surface with some barrier material. And then you do this electroplating, basically your copper processing. And then you remove the CMP, the chemical mechanical processing, planarization. Then you remove the additional copper, so make it flat. And then you thin down the wafer, okay, by grinding and etching. So then basically you get rid of those additional silicon. Then you make this copper wire through the silicon. Typically, the silicon will be thin down. The silicon wafer, as fabricated, typically hundreds of micrometers thick, a few hundred micrometers thick. And after this thinning process, you are going to reduce the wafer maybe to tens of micrometer or even a few micrometers thick. Okay, so then here is a real process, right? So here, this is more to the scale. For example, here you have your chip already fabricated, and with the front-end line and back-end line interconnects. And then you have this trench and pre-filled with some metal, like copper. And then you need to flip the wafer down, okay? And then have some carrier to hold the wafer. You have some glue to hold the wafer. And then you do the thinning from the top. You get rid of those additional silicon, thin down, and then you really make this trench exposed. And then you can have the bonding pad here. So in this case, this is a micro bump processing. So you add some micro bump material here. So I believe this is the TSV in the middle. There are different kinds of process: TSV first, TSV last, and TSV in the middle. So I will not go into the details because Realtek you have those packaging courses you can take. Okay. So here are some typical parameters for the TSV. Essentially, it will introduce your RC prosthetics. Okay. For the signaling, then you will introduce RC. And typically they're in this range. The resistance is pretty small, but the capacitance is quite significant. Okay, like tens of femtofarad. And then the dimensions, right? The TSV typically like 20 micrometer in terms of the pitch. From one TSV to another, you can have like a 20 micrometer. If you do more aggressively, you can have below 10 micrometer today. And then the typical aspect ratio here, like 5 to 20 in terms of H and D. Okay. So now if you have the TSV, then you can do this 3D bonding. And before you do the 3D bonding, then there's another intermediate step that is 2.5D. So 2.5D that means you have different chips like your processor and memory. And then you can have some substrates here to host the processor and the memory. And then here, this substrate typically is silicon, and it's called interposer. You can also go through this silicon interposer to have the power or signaling from the package. Okay. But then on the interposer, you will also have horizontal wiring to communicate between the processor and DRAM. So this is like an interposer. And then there are two kinds of 3D. One is, of course, you need the TSV first. And then depending on the bonding, there's one with micro bump, and there's another one with hybrid bonding, which is bumpless. So here first, for the TSV with the micro bump, right? You can have different DRAM dies, and then between the dies, you have this bump, okay? You know, if you have ever soldered your chip, right, you need to have something, right? In your lab, right? You add some this kind of alloy metal, right, as a bond. Then you bond those chips, okay? But here in this case, this is micro bump. It's much smaller than what you manually do when you do the wire bonding in your lab projects. So this one micro bumps has the dimensions like tens of micrometer, like 20, 30 micrometer. So it's really micro bump, okay? But still, you need to add something here, okay? Add some metal alloy here. And then for this bumpness hybrid bonding, okay, this is really copper to copper pad direct bonding. You do not add additional metal in between. So the metal pad, which is copper, from the dies will talk to each other directly, okay? With hybrid bonding, sub 5 micrometer pitch is possible. So here with the micro bump, you are talking about like 20 to 30 micrometer in terms of the pitch. The the distance between the adjacent TSV. So the hybrid bonding is the next generation in terms of the resolution of the pitch. Okay, so then if you look at the entire landscape of this advanced packaging, and this was borrowed from iMac. So you may have this on the larger pitch size, you may have the system in package stuff. You can have multi-die packaging and so on with embedded die and so on. And then when we talk about the micro bump, we are looking at this dimension, 20 micrometer, as I said. So you can have the micro bump with 20 micrometer. And then you can also look at the hybrid bonding, right, which will give you a few micrometer pitch. And here we are looking at, for example, die stacking versus wafer to wafer bonding. Okay, wafer to wafer bonding will give you even smaller resolution because it's more difficult if you already cut your wafer into small dies, and if you do die to die bonding or die to wafer bonding, then the alignment is more challenging. Okay, that's why the pitch is larger, maybe a few micrometer, even with the same hybrid bonding approach. But if you do the wafer to wafer hybrid bonding, you can really go down to like 1 micrometer or even below. If you have wafers, you do not cut, you have 2 wafers, and then it's easier to do the alignment. Then you can get even less than 1 micrometer bonding pitch. So this is entering so-called nano TSV region, which we talked about before, which is used for the backside PDN, backside power delivery network, using the nano TSV there. And then, of course, the ultimate 3D is transistor stacking. That is, this CFET, MOS on top of PMOS stuff. But that's not bonding. That's sequential processing. Silicon, germanium, and growth. That's not bonding. So if you look at the TSV diameter and the aspect ratio, so here is let's say the TSV different kinds of diameter die to wafer bonding. Typically, you are looking at tens of micrometer, and wafer to wafer, you can really go down to a few micrometer or even below 1 micron. But then you have to thin down the wafer because aspect ratio cannot be very high. If you are doing like nano TSV, you are really looking at the aspect ratio of this one less than 5. So if your diameter is 500 nano, aspect ratio is 5, then the wafer thickness needs to be thin down to 2.5 micrometer thick. So there's a trade-off here. You have to shrink the silicon thickness to enable finer pitch. So this is a general trend for the TSV processing. So this is what we discussed before, from the micro bump to hybrid bonding. So micro bump, as I said, so you can do like 20, 30 micrometer pitch. So what you do here is you have the copper and the copper pad, and you do need to add additional stuff. In this case, like this tin, silver, alloy, and then as a glue, basically, to glue those 2 copper pad. So here then the hybrid bonding is direct bonding. So it's copper pad to copper pad, direct bonding. You make them contact, and then you have some processing to apply some, stress to glue them directly. So you can realize sub micrometer pitch if you do this hybrid bonding. So any questions? Okay, so here are more details about hybrid bonding mechanism. So what you have here is right? Two copper pad, and then when you make them contact with each other, right? And then you will apply some temperature to anneal, and then the silicon, because on the side you have silicon dioxide, they will tend to glue together, and also the copper pad will tend to become integrated. So basically, on the surface of this silicon dioxide, you will have some dangling bond with oxygen and nitrogen, because surface, silicon dioxide you have oxygen, but typically surface you have some you will absorb some hydrogen. So the key is that during the bonding process, you are going to release this hydrogen away. You only have the oxygen bond, then silicon dioxide will glue together. Okay, so then those are the advances from the packaging technology. And then with those with those progress, you can imagine the change in the memory subsystem. Today, we have the processor, and you have the L3 cache, and then you have a controller, and then you have the DRAM. Then they talk to each other horizontally through the interposer. And then the DRAM now you can stack with the TSV plus a micro bump. So you can have multiple DRAM, 2D DRAM dies vertically stacked. Then you can increase the capacity of the DRAM. And the future, okay, this is not there yet. This is a cartoon figure. The future is that we want to stack the DRAM on top of the logic, your processor directly. So then this will enable more dense connections between the DRAM and the processor. Because today here, we still need to travel horizontally from DRAM to the processor. So the number of wires here is limited. We will talk about the DRAM like HBM interface. Currently, HBM3, the I/O width is 1024, 1024. That means you have 1024 wires on the interposer. Every time you transfer 1024 bits, right? Previously, if you recall, we talked about DDR, the DIN, right? Every time you transfer how many? 64, right? So because pin size is very large, right? You can visualize, you can see that. And then you insert that to your motherboard. So here, we're going to have those wires connecting the DRAM to the processor through this is a silicon interposer. We can have much denser connection, but that is not the ultimate solution, because ultimately, if you stack, then those bonding pitch, right, it's much smaller, like few micrometer, as we just saw that. So this would be the future. There are many challenges. If you do this, the challenge could be thermal, because your processor is so hot, and then the temperature, will penetrate to the DRAM, and DRAM, the retention is very sensitive to the leakage current. With high temperature, your off current go up, then the DRAM retention will be a problem. So that's why this is not there yet. So here, this 3D stacking could really introduce the heterogeneous system integration, right? So we talk about the DRAM on top of the processor. You can imagine that you can put all kinds of different dies together. So here you can have even flash, memory and flash, and also and front-end circuits, and also CMOS image sensor, and so on. So you can have different dies vertically stacked. Then that creates this heterogeneous 3D system. Of course, thermal and power delivery will be the challenges, right? Because so here the system is always like this. No matter how many dies you stack, your power comes from the substrate, right? The substrate has a board. Then you plug into whatever outlets you have, right? Then the power comes from here. Then you have to deliver the power this way, all the way up. And then the heat generated needs to dissipate. So here, the board, you cannot go this way because here on top you will have this TIM, the thermal interface material, whatever you may have there. Then you have heat sink on the top, and you have the air cooling or liquid cooling or your air fan, or it's going to cool down the system from the top. Then if you generate the heat here, then it's hard to dissipate. So that's always the challenge in the 3D system design. You have the trade-off between the heat generation or dissipation and the power delivery. So basically, how do you get the power in? How do you extract the heat out? This is always the problem. Okay, so I think that's pretty much for today. And the next lecture, we will talk about the HBM standard and then the products. All right, so then that's for today. Thank you.